Let's talk about Chapter 28, processes used to fabricate composite materials. One of the positive benefits of composite materials is that the molds can be very complex. They can be crazy shapes, they can be large, they can be small. There's a lot of freedom in the kind of shapes you can make that would be difficult to make out of metal or wood or whatever. Occasionally, even though we have this capability, we'll still have to make multiple things out of composites and then join them together later. So if you think about a boat, you can make the hull in an open mold, but all sorts of fittings and the engine and the bilge, everything has to be put on later. So we'll talk about some of the techniques for doing that. Cohesive bonding is the most basic method used in composites. This is going to join materials through chemical action. Cohesive bonding relies on the capacity of something to stick to itself. So this is what we use when we do layup, forming chemical bonds with the resin itself and whatever filler or reinforcement is in there. The cohesive force is the strength of attraction between molecules, also called the intermolecular attraction. One example of a cohesive bonding is a sandcastle, right? You make a sandcastle on the beach. The sand is the filler material or the reinforcement, and then the water is the matrix. The water has just enough cohesive force to keep a damp sandcastle together. But if you've ever made a sandcastle, right, you make it and then say you just grab a lump of sand and you try to stick it to the sandcastle, it won't quite work because it's not all the same thing. That would be an example of secondary bonding, which we'll talk about. The water is not a great matrix because it evaporates, right? As the sandcastle dries out, the water leaves and then it just becomes filler with no matrix and it falls apart. If for some reason you had a vat of fiberglass resin on the beach, the sand would still be a great reinforcement. You just have to replace that matrix and you'd have a cohesively bonded structure. Cohesive bonding in the realm of composites can only be done before the fiberglass has cured. So when you're in the mold, before everything is cured, you can add attachments or this or that. After it's cured, it will be a different thing. It will not be a cohesive bond. This comes into play whenever you're doing composites. You got to know how long you have with that resin before it cures. So this goes into knowing how fast the initiator or the hardener will act. If you're halfway through something and the resin starts to cure, you can't finish it. There's no way to work, and everything you do after that will be a secondary bond. It won't be as strong as that initial cohesive bond. The next kind of bonding is adhesion bonding. This is also called secondary bonding. This is widely used, but it's a little bit more difficult to achieve really good results compared to cohesive bonding. Adhesive bonds are essentially glued together, although what you're adhering them with won't always be called glue. It could just be fiberglass resin. The most important things with adhesively bonding something are that the two surfaces to be bonded are in close contact and they're clean, dry, free of wax or anything that might make it not adhere. Almost all adhesives require a tight fit between the mating parts. The one exception is epoxy, which is just as strong whether it's clearing a gap or not clearing a gap. But things like super glue or wood glue will always need to be in close contact, and then the parts have to be supported. Most adhesives don't gain any strength for minutes to hours or even days. So that goes into the jig and fixturing to join things together. One of the problems with some things like polyester and vinyl ester resins is wax. Wax is added to the resin to do a couple things. It floats to the top and reduces styrene emissions and aid in curing. So resins can be bought with or without wax, it just depends. But this stuff, when it cures, will float to the top and it will inhibit things from adhering to it. So this has to be removed through usually abrasion or maybe a chemical means. Mechanical fasteners are often used with composites. There's special considerations with composite materials. Typically, many smaller fasteners are used rather than few large fasteners because composites can't handle spot loads as well as something like aluminum might be able to. Often in composites, wherever a mechanical fastener or a attach point or a lift point will go through, there'll be a strengthened area with more layers of fiberglass or even a foam core and a support region to handle that load. Another problem with mechanical fasteners is expansion and contraction. The fiberglass, the composite, and the metal in the fastener will expand and contract at different rates, and this can cause big problems depending on the size of the fastener, how many, where they're at. Another issue is galvanic corrosion. So you have to make sure all the fasteners and all the metal work in something, a composite, is the same or close enough on the galvanic spectrum so that you don't get corrosion when it's exposed to water. Typically, this is solved with a zinc anode. Sealants are often used with mechanical fasteners. Sealants are not adhesives, although sometimes adhesives and sealants can be the same thing. But in this context, they're just used to make something not leak. So they either keep water, dust, whatever in, or keep it out of the assembly. One benefit to mechanical fasteners is that they allow the assembly to be taken apart and put back together for things like maintenance. So to wrap up, cohesive bonding is the chemical action that occurs when the composite part is in the mold and it's curing. After that part is cured, nothing else can be cohesively attached to it. Anything after that has to be adhesion. When two parts are cured, they can be adhered together, but they can't be a cohesion bond.